Hello friends, I welcome you all once again. This is Dr. Gajanan Zadav. In this video, we are going to study about Fabry Perot interferometer. As we have already studied what is interferometer and different types of interferometer, and we have discussed Michelson's interferometer also. Now here we are going to discuss in detail about Fabry Perot interferometer. Now what is Fabry Perot interferometer? In this interferometer, interference fringes of constant inclination called Heidinger fringes are obtained by transmitted light after multiple reflections between two glass plates separated by a distance. So, Fabry Perot interferometer is basically a high resolving power instrument which works on the principle of multiple beam interference. The multiple reflection of light in the air film between two parallel plates produce sharp fringes of equal inclination. The fringes are localized at infinity. That means here in this interferometer, whatever the interference fringes of constant inclination are there, those are called as Heidinger fringes. And we know that Heidinger fringes are also called as fringes in parallel films. In these films, interference fringes are produced due to path difference between the overlapping rays. So these fringes are called fringes of equal inclination, and the fringes of equal inclination are also known as Heidinger's fringes. So here, this is nothing but the interferometer, which we call it as a Fabry Perot interferometer. Now, how it is arranged, what is the optical arrangement of the Fabry Perot interferometer? How it is constructed in another way we can say. This apparatus consists of two glass plates, that is A and B, accurately parallel to each other, which are separated by a distance D. The inner surfaces of these plates are optically plane and thinly silvered so that they can be reflecting 70% of the incident light from that two partially silvered glass plates. The outer faces of these plates are also parallel to each other but inclined to their respective inner surfaces to avoid interference effect due to multiple reflection and refraction. So this is how this particular Fabry Perot interferometer is arranged. Later on, these rays of light which are becoming parallel to each other, that is multiple rays, beams, will fall on this particular lens, and this lens works as a collimating lens. This lens will collimate all these rays of light and it will converge on this particular screen. So this is the apparatus of Fabry Perot interferometer. Now working, how does this particular Fabry Perot interferometer works? Now if you look at this particular diagram, then you will find that there are two plates, glass plates A and B, which are accurately parallel. Here there is incident light which is falling on these two glass plates, which is kept from each other at a distance D, making an angle theta. After falling this on these two glass plates, multiple reflection takes place, and then all these monochromatic rays is rendered parallel by the collimating lens L1. Each of the parallel rays suffers multiple reflection in the air film enclosed between the plates A and B and emerge from the second, that is B. So this is how this particular Fabry-Perot interferometer works. So this is the lens. Multiple reflected rays are out of phase by a constant increment increasing the sharpness of the interference maximum. When focused by a lens, the interference fringes form concentric circles, higher orders towards center. So condition for maximum, as we know, that is 2d cos theta is equal to m into lambda. This is the condition for the maximum. Now here, in a simple way, we can say that there is an S, which is an extended source of monochromatic light, and convex lens L, which makes the rays parallel to each other. One of the rays incident on the parallel plate suffers multiple reflections, which is shown here in figure, and hence incident parallel ray produces a large number of parallel transmitted rays. The phase difference between any two successive transmitted waves is constant, and these transmitted beams are focused by a convex lens in its focal plane where they interfere with one another. Now here, if you look at this particular figure B, then you will find that this is how the intensity of transmitted beam takes place, or how the intensity changes. There are two plates A and B of a Fabry-Perot interferometer, which is shown in this particular figure. It is clear from this figure that the intensity of successive parallel beams will go on decreasing and depends upon the reflecting and transmitting powers of the silver coated glass plates. So here this is input light, this is the mirror surface faces of each other and getting reflected, multiple reflection takes place, and here at each angle light interferes either constructively or destructively. So this is the working of this Fabry-Perot interferometer. Now how the fringes are formed. Let D be the separation between the two silver surfaces, and theta is the inclination of particular ray with the normal to the planes. The path difference between any two successive transmitted rays corresponding to the incident ray, let us say it is 2d cos theta. And we know the condition for these rays to produce maximum intensity, that is already we have discussed, is 2d cos theta is equal to m into lambda, where m is an integer. The locus of points in the source which gives rays of constant inclination theta is a circle. So this is how the fringes are formed. Now what are the applications? Fabry-Perot interferometer is used to determine the wavelength of monochromatic light. Let us say lambda is equal to 2 of x2 minus x1 upon n, whereas lambda is the wavelength and n is the number of fringes. If we measure x1 and x2 and number of fringes, and if we substitute that particular value in this particular equation, then we can determine the wavelength of monochromatic light which is used here in this Fabry-Perot interferometer experiment. Now the second application is we can measure the difference in wavelengths also. Let us say we have used two wavelengths, that is lambda 1 and lambda 2. So lambda 1 and lambda 2 can be written as lambda 1 into lambda 2 divided by 2 in bracket T1 minus T2 minus T1. Here this can again be written as lambda squared mean upon 2 of T2 minus T1, because both the waves are same. That is, wavelength of both the light is same. Now, how do we compare Fabry-Perot interferometer with Michelson's interferometer? As we have already discussed that Michelson's interferometer works on two beam, that is, it is a two beam instrument, whereas Fabry-Perot interferometer is a multiple beam instrument. This is the basic difference between these two. But let us study some more differences, comparison between these two. The first one, the Fabry-Perot fringes are obtained due to multiple fringes, multiple beam interference, while Michelson's fringes are obtained due to two beam interference. Then the sharpness of Fabry-Perot fringes is very large as compared to Michelson's fringes. The resolving power of Fabry-Perot interferometer is much higher than Michelson's interferometer. Therefore, the two close wavelengths, sodium D1 and D2 lines, can produce well separated fringe patterns in Fabry-Perot interferometer. Thus, Fabry-Perot interferometer is used to study hyperfine structure of spectral lines. So this is the main difference between the Fabry-Perot and interferometer. Similarly, Fabry-Perot interferometer is very much superior than Michelson's interferometer, because in Michelson's interferometer there will be only two beams. Here there are multiple beams, and so that the interference pattern, the fringe pattern we are getting of Fabry-Perot interferometer will be well separated, and that's why it is much superior than Michelson's interferometer. So this is the comparison between Fabry-Perot interferometer with the Michelson's interferometer. Thank you so much, everyone.